Very good morning to all. I, Professor Ganesh Pai, Assistant Professor at the Department of Computer Science and Engineering, welcome you all to the sixth day of online short-term training program on machine learning for societal applications. Today we have with us morning session engaged by Dr. S. Murali and his research team on research issues and avenues in computer vision. Now I request Professor Saifuddin to introduce Dr. S. Murali to our participants.
Dr. Murali is president. He is a president of Maharaja Education Trust, Mysore, and is also the professor of Department of Computer Science, MIT Mysore. He is a president of 2 engineering colleges, degree colleges, 2 PUC college, high school college, and 2 MBA institutes. He has done his MTech, MBA, PhD degree holder, and also has over 30 years of teaching experience. He has successfully guided 16 PhD candidates and 6 are in progress. He has published more than 250 research papers in journals and conferences. He has conducted several conferences and workshops in image processing related areas and computer vision. He has delivered more than 100 guest lectures at various institutes and carried out 12 research projects funded by various funding agencies. He is having a patent in computer vision related to depth estimation. His areas of research include computer vision and image processing, and area of interest include philosophy. He is also the president of Kala Tapasvi, an art school. He is a managing director of Riverview Hospital and Mysore Paka. He worked as a chairman of Board of Studies and Board of Exams of VTU and Mysore University for Computer Science. He is a National Board of Accreditation expert and in the National Advisory Panel at LIC India for 2 terms. He worked as an Academic Council member of University of Mysore Governor nominee. He received Best IEEE Researcher Award, Dakshina Kesari Award, Software Ratnakara, Mandya Jilla Sahitya Parishat Award, Padmapura Taluk Sahitya Parishat Award. With this short introduction, I welcome Dr. Murali sir for the program. I welcome you, sir.
Thank you, sir. As mentioned earlier, morning session will be engaged by Dr. Murali sir and his research team. The topics being covered will be as follows. Dr. S. Murali sir will be covering on Introduction to Computer Vision. Dr. Deepu Singh, Professor in Department of Computer Science and Engineering, Maharaja Institute of Technology, Mysore, will be covering on 3D reconstruction. Professor Honnaraju, Assistant Professor, Department of Computer Science and Engineering, Maharaja Institute of Technology, Mysore, will be covering on lane detection algorithms. Dr. Avinash, an eminent industry expert in sensors and automated driving technologies, will be covering on automotive application of computer vision. Dr. H.L. Shashireka, Professor, Department of Computer Science and Computer Science, Mangalore University, Mangalore, will be covering on natural language processing of Indian languages from computer vision perspective. Dr. Geeta Kiran, Professor and Head, Department of Computer Science and Engineering, Malnad College of Engineering, Hassan, will be covering on application of computer vision in agriculture. Dr. Mohan S., faculty member at the School of Computing, Information and Mathematical Sciences, University of South Pacific, Fiji, will be covering on tools and data set for computer vision and machine learning application. All the speakers of today's session are renowned speakers and academicians, but due to time constraint, we will not be able to present a detailed introduction of all the speakers of the session to our participants. With this brief highlight of today's session, I request Dr. Murali sir to take over the session. Over to you, sir.
Good morning to all of you. ಎಲ್ಲರಿಗೂ ಪ್ರೀತಿಪೂರ್ವಕ ನಮಸ್ಕಾರಗಳು. Conducting program is really difficult in today's context. That too, coordinating so many people and asking them to be there online all the time. And today is much more difficult because it is not only one session. Actually, for one session, there are many speakers. Interestingly, all my research scholars who are presenting today, they are not research scholars actually. They have all completed almost 10 years before. These people will be, explaining their role, what has been allocated to them actually. So therefore, you will have complete knowledge about computer vision. As soon as you get up in the morning every day, invariably you open your eyes and start looking at the world for each and every activity. Even when you go to your bathroom and do the brushing and come out and open the tap, you do any activity when you get up from morning 6 o'clock or whichever time you get up till you go to bed, your eyes are on all the time. You will be seeing, the scene, natural scene all the time. You'll be seeing images, videos all the time without any kind of disturbance. You'll be seeing it. But all these images which are taken 20, I mean, we say around 25 images are taken per second, and so many images you'll be taking. You're not really taking from the image, actually you are taking from the natural scene, which is basically in the form of 3D, which is in the form of 3D, three-dimensional, X, Y, Z. But what has been come to your eye in one of the eyes is basically a two-dimensional. It means as a human being, you will be associated with vision all the time except the time at which you'll be sleeping. What do you do actually? You take images. Say, for example, somebody has come to my room just now when I'm talking to you. I looked at that side. It means my eyes captured that particular object also, and my brain started working on that particular object also. I know that consciously I need to look at the camera for this session. At the same time, I also looked at this. I mean, I did, managing these two kind of things. It means which has managed this actually. This has been managed by my brain. It is always computing on the images, video that you capture through your eyes. This is human vision system. Human vision system, whether you want it or you don't want it, all the time, you will be watching continuously. You would have seen even in the examination hall, students will be looking at the top. I mean, they look at the top and they try to, download something from the wall also. Of course, it is not so, but they try to look at the top. So therefore, there will be no such of disturbance will be there. So therefore, the brain will be, at least able to compute whatever they wanted to recall from the memory. It means whether you want it or you don't want it, when you're driving in the vehicle or you're sitting alone looking at somewhere, whether you want it or you don't want, always the images will be there. How these images are coming? Images are coming from the natural three-dimensional scene. These are being processed in your brain. So that is why you require sleep, because your eyes are so much trained to work from morning till evening. So that's why you will be sleeping by closing your eyes. So therefore, no more capturing of this. This is very, very, very fundamental mechanism which is happening for any human. It's a God gift. Nobody has, done by artificially. It is all the natural thing which is happening to any human being for that matter. Okay, now parallel to this, if at all, if similar all these activities are to be carried out by machines, then it becomes computer vision. How exactly vision is there for a human being? A similar kind of activity, if you are being done by the machine, then it becomes a computer vision. Say, for example, right now in front of me, there is a board. I'm trying to read what are the contents of that by using a human vision system. Try to do a similar kind of reading from the printed thing which are there on the board or in the billboard or in the bus board or somewhere in the camera, somewhere on the scene, wherever it is, by using a camera, then it becomes a computer vision. So computer vision is a very, very similar activity, carried out by supporting of a machine. Machine does similar activity. So what all it does? It does everything like a human being. Like I do optical character recognition. Even for me, reading from the textbook, say for example, I try to read this book. How I read it? I open my eyes and focus it on this. Focus on a specific area. Now I cannot look this side and try to read. So therefore, to read this, I need to focus my eyes onto these pages. So therefore, if you are able to focus a camera connected to a computer and try to read operation becomes optical character recognition, but it is activity of a computer vision. Like I walk. How do I walk? I look at objects which are there around me. If obstacles are not there, for example, to move this side, to move this side, left side, I look at the objects which are there because my eyes are open. When my eyes are open, I try to look at the objects which are there around me, which are not obstructing me. So therefore, I can find myself a easy path. I move on. I am moving as a human being by using my vision system, supported by vision system, assisted by my camera, helped by my brain in a very similar way. A robot, you are making a robot is being made to move like that based on the capturing of the images kept taken from the camera, give it to a processor will do it. Now you would have seen actually there are a lot of driverless cars. It is basically an imitation of the human system. Say for example, recognizing people. So face recognition for that matter. Say for example, when our principal had come to my room, I identified because I take that object and identified. So face recognition, I do as a human being. Very similarly, machine does. So that's a face recognition. Eating, walking, doing anything that I do on this earth, it is all vision system. If I do similar activities, not necessarily by the same machine. If it is all things are done by the same machine, then it becomes human being. It is not human being. We are trying to imitate the individual activity, for example, optical character recognition, or it may be a robot path movement, maybe a language recognition being be explained by H.L. Shashiveka today. Maybe I'm trying to identify certain objects. Maybe Dr. Avinash will be speaking on how exactly the vision system is there for vehicles adopted in vehicles. And Geeta Kiran will be explaining about how exactly this will be used as in agriculture. So when I say computer vision applied to agriculture, the title itself looks appealing. But why you are not talking about a human vision system, working on agriculture? It is quite natural. I do agriculture. What is special in that? But how exactly I do agriculture? If I am able to give all the support inputs and try to give it to an artificial algorithm, then that becomes computer vision. Okay. Now, here in case of computer vision, I just stop only at this juncture. There are three things to be understood. One, computer graphics. Somebody will be already studied about computer graphics. But computer graphics, wherein already models are there. I am trying to generate an image. Of course, video means it's a set of images. So therefore, already models are available. I am trying to generate. Whereas in image processing and all, I try to take an image and try to do some sort of processing on that and generate another kind of image or maybe some kind of result out of that. Whereas in case of computer vision, it is just a reverse. I take the images and try to generate the models and try to generate the models which are required for me, because artificially I need to have a similar kind of 3D analysis on our vision system. So when I looked at the scene, I always looked at considering the entire scene is on a 3-dimensional. So therefore, I try to have images being taken and try to have a reconstruction of 3-dimensional objects by taking multiple kind of objects which are there in a 2-dimensional. Basically your eyes or cameras are basically taking 2-dimensional images of the scene. Scene is naturally, it is in 3 dimension, X, Y, Z. But when it has come to my eye or when it has come to camera, it will be 2-dimensional. So therefore, I need to bring it to in the form of 3-dimensional. Say for example, from here to door, how far it is there, I visualize, I compute myself, it could be around 20 feet. How did I do it? I did it by considering the images which are being captured by my camera, which are basically 2D in nature, compute this in my brain and assume I give a result saying that approximately 20 feet. So this is how I do it. If they are able to do a similar activity by using the machine, then it becomes computer vision, right? See, in this computer vision, there are three things that you got to understand. Then I request my next speakers to go on. One, the scene is always three-dimensional. What I'm seeing is three-dimensional, created through my two eyes, generating a three-dimensional view for me. But natural available thing is scene is basically three dimension, but 3D brought to 2D, processed in my brain, generated 3D visualization for me. This is thing you have to keep in your mind. If you are doing similar activity by using computers, take natural scene which is in 3D, bring it to camera, it gives you 2D, do some processing and do the third dimension processing. So this is how we are supposed to do. Second thing is, always what I am seeing on the earth, it's a God's gift. It is called perspective view. All views are perspective in nature. It means objects which are there closer to me appearing smaller, objects which are far away are appearing, objects which are close to me appearing bigger. Same object, when you take it away, the tree which is there 1 kilometer away from me looks smaller, but it is not so. This view system to be understood whenever you are getting into computer vision system. First thing, difference between three-dimensional and two-dimensional. Natural scene is 3D. God's creation is 3D. When you are taking into your brain, your two cameras takes two-dimensional data, process in your brain, generates 3D and gives it a three-dimensional visualization. So next speaker will be talking about how exactly a similar kind of three-dimensional objects can be reconstructed by using two-dimensional objects. Okay. So this is what, whenever you are getting into computer vision, so three things you have to keep in your mind. One, 2D to 3D, always this clarity should be there. Second thing, perspective view. The whole system is perspective. When I take my hand away, you can make out now itself, the hand is appearing smaller. When I just bring this hand close to this camera, hand is appearing bigger. As the object coming close to your point of view, point of seeing, then the objects are becoming bigger. But really they are not becoming bigger or smaller. It is only the view that you are generating in this camera or by using this camera. So therefore that you have to keep in your mind whenever you are getting into computer vision. And in computer, we are regenerating 3D objects to make certain analysis, because all these objects are always three-dimensional in nature. In two-dimensional, certain informations are not at all be understood. So that's why I'm taking multiple images and try to do the reconstruction of this. So thank you very much. Dr. Deepu, you can go ahead with your presentation.
Dear participants, our next speaker is Dr. Deepu Singh. He is professor in the Department of Computer Science and Engineering, Maharaja Institute of Technology, Mysore. He will be speaking on 3D reconstruction. Over to you, sir.
Very good morning to all of you. I thank my guide, Dr. S. Murali, for providing this opportunity to speak about my topic of interest, that is on 3D reconstruction. It was a dream since the invention of computers that they would be able to see and think. Though computers became faster and faster day by day, just its speed and memory were not enough to make that dream a practical. So in today's presentation, I will be about what is 3D reconstruction, the importance of it, and there are types of cues widely spread into monocular and binocular, and these following types, and under binocular cues, these three types. So let me explain the visual system. When the real world exists in 3D or more than 3 dimension also they exist, but we are interested in width, that is width of the object, x, and height is the second dimension. The thickness of object or the camera to the object. You can see a lot of different terminologies that are used here. Is the camera point. The camera is nothing but eye. The real world 3D objects fall on the picture plane. Picture plane is the plane of camera or the eye. 2D picture plane. The third dimension is lost. And there are many we can reconstruct the lost third dimension. We will be speaking about those. The different are here, like this. This is horizontal plane. Different applications of 3D reconstruction. You can see here. We have capable of doing of humans, but making machines is still a challenging job for engineers. Adding vision to machines, information about surrounding environment. In the accurately detect defects in manufactured parts with no human intervention. To recognize people before opening to allow authorized people into the office.
Here, the very first figure shows Mars rover, which is sent to explore the planet Mars, that used stereo cameras as vision sensors for understanding the environment by analyzing the images taken from them. The next, while sending vehicles to other planets, the weight of every vehicle becomes very important. So as much as possible, we need to reduce the weight. So instead of sending two cameras, if we reduce it by one, that is also going to that will also contribute. So reduction in the number of cameras to acquire third dimension is quite important. See the next picture is an autonomous robot which tries to navigate in the path. Even that uses the information like depth. It can be used for navigation by a blind person in space. Now there is an automated vehicle. The classification of vehicles based on whether they are two-wheelers or four-wheelers, how far they are from the camera, all those informations become very important. So in all these places, we can use the third dimension. See, I am explaining about different cues that are used to extract the depth. See, depth perception, vision is the most important perception sense in obtaining information from surroundings. Depth perception is the visual ability to perceive the world in 3D and estimate the depth of an object. Knowledge about physical objects and scenes can be obtained from a visual input. In 3D, first dimension is width, usually referred along x-axis. Second is height, which is usually referred along y-axis. And the third dimension is the depth or distance parameter, which is usually referred along z-axis. But when cameras capture and projects the real world scenes onto a plane, the third dimension is lost due to perspective projection. Different terminologies used in projective geometry, where projection of how real world entities onto a viewing plane of an eye or image plane of a camera can be shown. The diverging visual rays from the objects passes through a vertical imaginary plane called view plane. So whenever a scene is viewed using a camera or eye, depth information can be estimated because of certain following cues. They are called as monocular cues. The very first one is the Motion parallelogs. Whenever a person moves, objects that are closer seem to be moving in opposite direction faster than objects which are away from us. You must have observed this while driving or while traveling. The speed at which objects move gives information about the relative depth of objects in a scene. From the information about the direction and velocity of movement, depth can be obtained. This figure, the very first figure of car, indicates this effect while moving in a vehicle. Motion parallelogs is the technique used to perceive depth by some animals that lack binocular vision due to their eyes having little common field of view. The next figure indicates depth from motion. When we move towards an object, it seems to be expanding in our view. Over a period of time, the retinal projection of an object expands, leading to the perception of movement in a line toward the observer. This phenomena is also called as depth from optical expansion. The dynamic stimulus change enables the observer to perceive the distance of the moving object. The changing size serves as the distance cue. Next, what we have is kinetic depth effect. This skeleton structure of a solid object where every edge is replaced by a wire is called as wireframe model of an object. If wireframe model of an object is placed in front of a light source so that its shadow falls on a translucent screen, an observer on the other side of the screen will see a two-dimensional pattern of lines. When the object rotates, the visual system will perceive the third dimension from the movements of the lines. This figure shows an example of kinetic depth effect. This effect also occurs even if the rotating object is solid, provided that the projected shadow consists of lines which have definite corners or endpoints. The next, the parallel tracks, railway track that you see is an example for linear perspective cue. Our eyes exhibit perspective vision. Due to this, remote objects seem to be smaller than the closer objects of same size, as visual angle of an object decreases by increase in depth. As depth increases, the visual angle decreases. That is the common phenomena of our eyes and cameras. The visual angle of an object is the angle subtended at the eye by a triangle with the object at its base. The height of this triangle is more and visual angle is small when distance of the object from the eye is long. For example, whenever parallel edges are viewed orthogonally, they seem to meet at a remote point called vanishing point from the viewer. The property of parallel lines converging in the distance allows us to reconstruct the distance of an object or of landscape features. An example would be a railway track as shown in this figure, which seems to be meeting at a remote point when viewed orthogonally. This remote point is called as vanishing point. Distance of objects from viewer can be obtained with respect to vanishing point. The another monocular cue that you can see here is aerial perspective or atmospheric perspective. Fine details are visible in an image that has high contrast. The nearby points are with high contrast, whereas if you go deeper, if the distance increases, there is no much contrast. Everything looks like same when the distance is bit long. As object distance increases, contrast in an object decreases with the background due to scattering of light into the line of sight as shown in this figure. Due to this, images seem hazy and as they are away from viewpoint. This is called as distance fog or atmospheric perspective. As a result, foreground possesses high contrast and the background possesses low contrast. This gives information about relative depth of the object in a scene. Now, the next binocular cue is with occlusion. It is called as occlusion. Whenever an object covers other objects, faraway objects become partly or fully invisible. Fully invisible objects cannot be seen, whereas partly visible objects can be treated as relatively far objects with front objects. This is called as occlusion or interposition. However, this information only allows the observer to create a ranking of relative nearness. The presence of monocular occlusions can be identified by noticing different objects' texture and geometry in this figure. So this object is very close to the camera or the viewer, whereas this is bit far. You can see the black object is too far compared to this, and this is bit far compared to this triangle. So the next monocular cue is with, it is called as elevation. When objects of same heights are viewed, objects at remote points look smaller. When pillars of same height are viewed from different depths, their height seems to be different. You can see that in this figure. When an object is visible relative to the horizon, we tend to perceive objects which are closer to the horizon as being further away from us, and objects which are further from the horizon as being closer to us. This difference in heights provide relative depth information. And the next monocular cue for depth is this texture gradient. This figure depicts the case where fine details on nearby objects. This figure gives fine details for nearby objects. The nearby points are having more clarity compared to the faraway points. Texture gradient is the distortion in size which closer objects have compared to remote objects. Objects' pattern seems to be denser at remote space. For example, on a long gravel road, the gravel near the observer can be clearly seen of shape, size, and color. In the faraway space, the road's texture will have less clarity. The next monocular cue is with lighting and shading. When light falls on an object, some portion is absorbed by the object, whereas remaining portion is reflected. This reflected information defines the object in view. The way that light falls on an object and reflects off its surfaces and the shadows by objects gives an effective cue for the brain to determine the shape of objects and their position in space. This figure specifies the light and shading in depth perception. And the next monocular cue, you have tried this while capturing images from your camera. You would like to focus specific points. So this is called as defocus blur. Blurring relatively an image at portions belonging to different depths is very common in photographs for establishing the impression of depth. When we look at certain objects, points closer to that object will have more clarity as they are at focal length compared to other points. So other points seems to be blurred. These flowers, other than this main flower, seems to be blurred because they are at some other focal points. So other points seems to be blurred. This difference in focus, defocus values gives relative depth perception. Now we move on to the binocular cues. Binocular cues provide depth information when we view a scene with two eyes or when we use two cameras. Binocular cues are more powerful and accurate in providing depth information than monocular cues. So we have the three main binocular cues. This one is monocular only. The very first one is stereopsis or retinal disparity, or we call it as binocular parallelogs. Stereopsis is a phenomena wherein two eyes are used to view a scene, and by using two images of the same scene obtained from slightly different positions. So we are all blessed with two eyes, but both the eyes are at different place, which capture different image of the same scene. Thereby, a kind of processing happens in visual cortex of brain on these two captured images, where both the images are merged to find out the depth. It is possible to triangulate the distance of an object with a high degree of accuracy. Each eye views a slightly different angle of an object. You can see the left eye and the right eye, they see the same scene but slightly differently. So each eye view a slightly different angle of an object. This happens because of the horizontal separation of the eyes. If an object is far away, the disparity of that image falling on both retinas will be small. Disparity will be small when the depth is high. If the object is closer, the disparity will be large. This figure shows two images of same scene. First one is viewed of left eye and second image is viewed from the right eye, which seems to be moved slightly due to change in the position of eyes. Some rangefinders work on this principle during situations like deer hunting. They provide high accuracy in aiming. Even battleships use binocular disparity in order to find the range, but the lenses are widely separated and the ranges are measured in miles. Now the next one is binocular convergence. This. When we view a pencil or any object moving slowly towards our eyes, as in this figure, we can feel strain in our eye muscles. Only at certain point, objects will be in focus and both views converge. When object is closer than this point, convergence exceeds, and when object is far away, convergence is insufficient. As a result, at properly converged point, object seems to be clear. If we move the pencil within that short range, muscle strain caused by eyes due to its rotation inward to their limit. Because of stereopsis, the two eyeballs focus on the same object. In doing so, they converge. The convergence will stretch the extraocular muscles. As happens with the monocular accommodation cue, kinesthetic sensations from these muscles also help in depth perception. This is called as binocular convergence, which serves as cue for depth perception. The angle of convergence is smaller when the eyes is fixing on remote objects. Now the last one is with it is called as shadow stereopsis. Fusing images of same scene but with different shades can help in depth perception. So this is called as shadow stereopsis. Shadows are important stereoscopic cues for depth perception. And here, this is not binocular cue, it is a monocular cue where the parallel edges meeting at some remote point, they seems to meet, but they don't meet. But in image, if they are extended, they will meet at some point, which we call as vanishing point. They give depth information about different space, different objects in the image. So that's about different 3D reconstruction or different cues for 3D in an image. Thank you.
Thank you, sir. We have our next session engaged by Professor Raju, Assistant Professor, Department of Computer Science and Engineering, Maharaja Institute of Technology, Mysore. He will be speaking on lane detection algorithm.
Good morning, Ananda. I thank my guide, Dr. Murali sir, to give me an opportunity to speak on ADAS, that is a line departure warning system. In the presentation, there are two images. The two images depicts the content of my presentation. Okay, the first figure indicates ADAS. So ADAS means Advanced Driver Assistance System. So we can see in this image, there's a digital numbers. It indicates the ADAS system consists of digital technology, means cloud, machine learning, deep learning, artificial intelligence, computer vision, and different types of sensors. So ADAS is an electronic system that assists the driver in driving and parking safely. Okay, that is the main objective of ADAS. Then in the second figure, it indicates the line departure warning by using a computer vision algorithm, that is a line departure warning with monocular camera. So the above image indicates the warning when the car move away from the lane. Okay, that is about the my presentation. So I am going to explain you about the line departure warning system. It is a computer vision based system. So according to the market of ADAS, the market has projected to reach 91.80 billion by 2025. So this trend clearly signifies the rising popularity and market acceptance of the innovation ADAS system. So the ADAS consists of different sensors, actuators. So here, one of the important component of ADAS is a vision-based system. So mainly vision-based system is used for detecting pedestrian, detecting front vehicle, identifying surrounding vehicles, and even though identifying road signals. Like that, there are many operations can be performed by computer vision or vision-based system. So sir has highlighted the different applications of computer vision. So this is one of the important application of computer vision. So here, these are the components of ADAS, means automatic advanced driver assistant system. So it consists of mainly 5 different types of sensors. One is long range radar, LIDAR, cameras, short and medium range radar, and ultrasound. So here in this presentation, I'm explaining only on the vision based system. So the cameras are the main eyes of advanced driver assistant system. So there are different types of cameras the ADAS consists. One is a monocular camera, other one is a stereo camera. So monocular camera is mainly used for detecting a front view of the vehicle. So by using that, it detects the pedestrian, it also detects the lane departure, and it also identifies and recognizes the road sign signal. So we observe there are a lot of road signs present in the road that indicating speed limit. Okay, some places is put 50, 30. In some places there is a signal indicates there is a school zone, and there's a zone not horn. So there are different areas, the different signals. So the ADAS system will identify those signals and take preventive actions based on the signal. So if the signal indicates that it's a 30-kilometer speed, then the system automatically indicates the driver to reduce the speed. So like that, the different operations is performed by the front camera with vision processing system. Then the surrounding camera is used for identifying the surrounding vehicles. So it also contains the sensor to measure the distance between the surrounding vehicle. So similarly, there's one more camera at the rear side. It is used for assisting the parking along with the sensors. So sensors, by using the camera sensor, the ADAS perform different activities. So mainly it consists of ADAS consists of mainly 5 different components: sensor, software, actuator, processor, and mapping system. So sensor is an important component of ADAS. So sensors are used to ensure that adequate safety measures are taken based on specific situation. Example, if there is an hump or if there is a vehicle, if there is an obstacle. So in order to identify the obstacle, the sensors will be used. So the sensors are radar technology, are visible sensor, or ultrasound sensor. So sensor will extract the information of the current situation, then that information will be sent to the processor. So the processor will perform and it will take the corrective actions based on the sensor data. Next component is the software. The software is considered to be a backbone of the hardware function today. With changing the customer expectation, almost every company relies on much on software as a software. So its main concern is the software development. So that is the software component. The actuators, so once the sensor extract the information and the software process the data by using processor, then based on that information, the actuators will take the action. Then the processor, a processor processes all the information extracted from the sensor, then it sends signals to the actuators. The last component is the mapping system. The geographical and infrastructure information is generated, stored, and uploaded via sensor to a given vehicles to perform exact function and its location. So I already mentioned the ADAS contains the cloud environment for storing the data, and it uses sensors for extracting the data. Then to perform the action and to perform the process, it includes artificial intelligence, machine learning, and other vision-based systems. Okay, now what is a vision-based advanced driver assistance system? So vision-based ADAS uses embedded vision or computer vision systems to identify and track the potential hazards on the road and provide a real-time vision-based analytics to the driver. So through the vision, the ADAS will identify the objects in front of the car or surrounding the car or backside of the car. So it will give an image or video sequence to the system. Then the system will process the information and it will give a real-time information to the driver. If the driver wants to take the vehicle reverse, then the rear camera will capture the images and it will process. Then it will give information about if there is any obstacle, or it is also gives a data about the distance between the obstacle and the vehicle. And similarly, the surrounding cameras will give information about the surrounding vehicles, how many vehicles are present in the surrounding and what is the distance between the surrounding vehicle. So I already mentioned there are two types of camera the ADAS contains. One is a monocular camera and the stereo camera. So stereo camera is mainly used for estimating a 3D information and is also generate a 3D view of the surrounding. To generate 3D view of the surrounding, the stereo camera has been used. Okay, these are the common application of vision-based system. One is road sign detection, lane departure detection, pedestrian detection, vehicle detection, vehicle localization, or traffic lane detection, emergency braking system, forward collision warning system. So all these functions are performed based on vision-based system. So here are some of the applications of the vision-based system. Here there's a car, it will detect the signs. Okay, now you can see here, there's one sign indicates the movement, the lane or the road is belongs to the car moving. And similarly, the one more signal specify the speed, that is 70 kilometers. Like that, the sign indicates the different information. That information can be extracted from the camera information. Similarly, the pedestrian detection. So The vision system identifies the pedestrian and it also gives a distance between the car and the pedestrian. So based on this information, the driver can apply brake or he can slow down the movement. Then there's one more application, lane departure warning system. So if the vehicle is moving towards the right side or left side by checking the lane departure. There are one more applications, traffic lane detection system. Okay, these are the applications of vision-based system. Next, one of the important application of the ADAS is the lane departure warning system. This is a vision-based system. So lane departure warning is one of the important feature of advanced driver assistance system, which aims to improve overall safety on the road. So it consists of a lot of challenges. Sometimes the lane is not visible. Sometimes there is a vehicle on the lane. Then there will be a shadow. Like that, there are different challenges need to be faced when performing lane departure warning system. So the challenges such as inconsistent shadows and fading lane marking often flag you. The road surface cause the lane detection system to produce a false warning. Then one more challenge is the user may disable the functioning. Users are aggravated by the warning and tend to disable the safety feature. Okay, in this figure indicates the alarm of the line departure warning system. So here, when the vehicle departs from the lane, it sends three different types of signals. One is the visual signal, one more is alarm, and one more is the vibration. So here you can see in the second image, once the vehicle departs from the lane, it automatically send a signal or it automatically gives signals to the driver. Okay, one more challenge when using ADAS is the environmental challenge. So you can see here the bottom two images of the same scene with different environment. So in the first image, the road is clear. Here we can extract the lane, but in the second image, there is a snowfall. Then in this situation, it is very difficult to extract the lane. So here in India, during 2019, there were 437,396 accidents were occurred and more than 160,000 people were killed due to accident. Similarly, in Malaysia, 548,598 cases of accident were reported in year 2080. So some of the accidents are not reported. So accidents are occur due to traffic or due to high-speed driving. So like that, there are many situations the accidents are occur. Okay, the lane departure warning system overview. So here the main source of the lane departure system is a camera. There is a monocular camera. Then the monocular camera along with the processing system, inbuilt computer. The computer processes the images extracted from the monocular camera. So the lane departure warning system consists of mainly three steps. One is lane detection, lane tracking, and lane departure. So first important step is the lane detection. So lane detection system consists of the 5 different steps: image acquisition, pre-processing, edge estimation, strips identification, and line fitting. So first, the image acquisition. So I already mentioned the monocular camera will be used for extracting the images. So the monocular camera extract the images. Once it extracts the images, the image may be blurred, or image may consist of noise, so image may not clear. So to improve the appearance of the captured image, the next step is the pre-processing. So in the pre-processing step, the filtering operation will be performed, or enhancement operation is performed. So if the image is not clear, in general, we use a contrast stretching function to improve the appearance of the image. If the image consists of noise, so we use a filtering operations to eliminate the noise from the captured image. Okay, there is a second step of lane detection process, that is a pre-processing. Next is the edge estimation. So once we pre-process the image, the next step is to identify or detect the lane on the road. So we know the lane. So there is a white line on the road. So here we need to segment, or we need to extract the lane from the road. So usually we know the road color is black and lane color is white. So we need to extract the lane from the background. Sometimes the lane is covered by the vehicle or covered by some mud. So from that, we need to extract the lane. So to extract the lane, usually edge estimation algorithm will be used. There are different edge estimation algorithm, like example, robot operator, pivot operator, Sobel operator, canny edge operator. Different types of edge operators can be applied to estimate or to get the edges. So when we extract the edges may include some noisy edges or unwanted edges. So in order to eliminate the edges or wrong edges, the next step is the strip identification. So once we detect the edge, so you can see in this image, there are a lot of black pixels on the segmented image. You can see here, there is a black patches. So here the black indicates the foreground and white indicates the background. So here we need to extract the region which consists of black lines. But here in the middle of the image, it consists of some black spots. So there's this noisy edges. So we need to eliminate this noisy edge. So in order to eliminate this noisy edge, next step we use is a strips identification. So here to identify the lines, off transform can be used to extract the lines. So here after extraction of line strips, the lines are clearly visible. So there's a left side lane, right side lane, and the middle lane. So in order to identify the lane departure, these lanes are very important. So based on the central line, right line, and the left line, so the departure system is work. So once it is identified, next is the line fitting. So in the line fitting, the sequence of similar tokens are joined and it generates a solid line. So this is the last step of the lane detection process. Next is the tracking process. Once the lane is detected, then the lane is tracked, because when we when checking the lane departure, the lane tracking is very important. So we need to follow the lane, and we need to, the car has to maintain the distance between the left lane, right lane, and the middle lane. There are different approaches used for the tracking. So tracking is a concept. In general, tracking of an object in a video is defined as a problem of establishing the correspondence between the same object identified in the subsequent video frame. So in the first frame, the object is identified. In the tracking process, in the next frame, the same object need to be identified. If the object is not present in the second frame, then the object is missed. So we need to identify this object in the subsequent frames. So in order to identify, in order to track the objects, there are different algorithms. So there's one algorithm is recursive filtering and subsequent n frames and Kalman filter. So there are two different approaches can be used for tracking the lane. So one of the popular approach is a Kalman filter approach. So here I have not include the equations of Kalman filter. So just mentioning the filter technique. So either It can be used recursive filter or Kalman filter. So once the tracking is performed, the last step is the lane departure warning system. So the figure indicates the lane departure warning system. So here, this yellow box indicates the vehicle, then there's a left lane and the right lane and the center lane. So the departure warning is performed based on the middle lane. So lane departure warning is set based on the angle value between the middle horizontal axis and the road lane boundaries. Okay, here left lane and right lane indicates the boundary of the road and the middle lane. So here we first it calculates the angle of the deviation. Here the threshold will be set. If the angle is above the threshold, then it generate the warning information. So here E2 and A1. So here the angle will be extracted, then the angle will be checked based on set threshold value. Once this angle is above the threshold value, then it sends a lane departure warning system. So either it may be a departing left lane or the right lane. So here the two angles will be considered, angle 1 and angle 2. So angle 1 for left lane and angle 2 for right lane. So once it exceeds the threshold value, the alarm, the alert will be sent. So the alert or alarm may be at three different ways. One is the visual information, audible information, or vibration. So visual information means the tracking information or the departure information will be shown on the display screen. Audible's alarm is the alarm or the voice signal by indicating the vehicle is departing left lane or the vehicle is departing right lane. Or the last one is vibration, either to generate the seat vibration or other form of vibration. So based on the three alarms, the driver can take a decision. So based on this information, the driver can take the primitive action, so it can also avoid the accidents. Okay, you can see in this diagram, there are three types of alarm. One is a visual alert, audio alert, and the vibration alert. Okay, this is the overall system, lane departure warning system. So here the camera mount, that's the camera unit. So camera regularly captures the images. So in general, 30 frames per second. So the camera will capture the 30 frames per second. Then each frame will be processed. Then each process will be perform the same step, that is lane detection, then lane tracking and lane departure warning. So based on that information, the buzzer will be performed or indicator. So in the indicator, the display unit, in the display unit, it will show the warning, whether it is departing or normal. Then there's a switch, that is vibrating switch. Okay, this is a block diagram. This is a sample video of lane departure warning system. Okay, thank you.
So, dear participants, our next speaker will be Dr. Avinash. He's an eminent industry expert in sensors and automated driving technologies. So, he'll be addressing on automotive applications of computer vision. Over to Dr. Avinash.
Thank you, sir. First of all, I would like to thank Murali sir for providing this opportunity to speak here. Um, and also Honraju sir, probably my presentation is an extension of what you have presented right now, but more practical in nature. Right now, I currently come from Continental Automotives, and I have been working into this ADAS business unit, and ADAS, that is the Advanced Driver Assistance System business unit. So I will show more of practical applications and what we did in Continental. So I was heading the camera department in Bangalore for the global operations, and then moved to Germany, and I was heading the program management department for the camera department there. So Continental here, you can see on the right hand side, there is a picture of an animal called as lynx, and that is the logo of Continental ADAS business unit. ADAS, that is the advanced driver assistance system unit. Here, why this animal? I just wanted to give an introduction there, because this animal has a very it is called lynx, and it is having a high perception of sensory organs. So the eyes, it can see in a very dark light very well, and also it has a very good sense of uh, other sensors like radars, means in the concept of the radar sensors and so on. So ADAS business unit, the Continental business unit, they contains cameras, radars, ultrasonic sensors, and also the lidars. This is the wide range of portfolio in the business unit of ADAS, and I come from the camera department, the camera business part of it. So I was with Continental for about 6 years until last week, and I moved to a different company this week. So, but nevertheless, I'm just talking about what I did there. So there in the camera business, we had three different products. That is the smart cameras, the satellite cameras, and the advanced driver control unit. So the driver control unit, it is the processor board on which all the algorithms actually run. And the satellite cameras are the cameras which contains only the optronics part of it, the lens, the imager, the circuitry which connects to the computer kind of circuit. So they don't really process anything in the satellite cameras. That is the ones which you can see in the middle. And the above the picture you can see is the camera, the smart camera, wherein the processor board is also embedded along with the optronics, that is the lens and the imager, uh, in one box. And this gets fitted into the uh, inside windshield behind the inside rear view mirror, and that's where this smart camera is located. Whereas the satellite cameras, they get situated all around the cameras and also at different locations. I'll show it in the next picture. And mainly the ADCU down below here, you can all the algorithms, the smart part of the camera, what it does happens in this electronics. The software runs on this electronic. So with these combinations, we have our means we had uh, different products can be managed to be developed. Either we can develop a mono camera, which is a smart camera with some premium features in it, or very less features also we could deliver. What are those features? I'll come to that later. And then we can combine with a different combination of cameras and ADCUs to create a product which can be delivered to our customers. And our customers, basically, they are the OEMs. Any name a car company, and they're all our customers. Most of them are like Audi, Mercedes Benz, and Suzuki, and Toyota, and there are many other OEMs. They are our customers. So we were the tier one companies. We used to provide the components of the to these companies. So what does this camera do? So we had the fifth generation cameras, the smart generation cameras, and we had the cameras looking at the rear side of it also. So they were called as the rear view cameras. And also in the previous slide, as I showed, there were satellite cameras which were not doing any processing, but they were just looking at all around the camera. So this is a slide of the rear view camera where you can see the size of the camera. It is not bigger than just 1.5 inch by 1.5 inch maximum. So the entire box they get just fitted inside the logo of the backside of the car. So even now you can see these rear view cameras fitted in most of our Indian cars, but they don't have the smart features in it. They just look means they just see the back part of the camera and give a view to the driver who is driving. And with that view itself, the driver can easily park the car, and so much he can do. But what if the camera can also means of course it is small. What if it can also detect a human being, a pedestrian, and alert the driver saying that there is a threat? Maybe a child is just running behind the car, and you might have to brake in between. Such things can also the camera can also do, and it can also brake if it needs to be done. And then you can also maybe this is not a practice in India, but this is a practice in Europe and USA, that there is a trailer hitched onto the car. So when the trailer is hitched and this trailer um, is not actually it is like a bogie to our to an engine, and it doesn't always move according to your wish. Like if you want to back up the car, trailer will go in one direction while you're parking it in another direction. So you will always get it will always be a problem to park the vehicle in the backup mode when there is a trailer connected to the car. So this smart camera can also assist in such a case to easily park the car even when a trailer is connected to the car behind. So these were some of the features that have been integrated into the rear view cameras. Similarly, okay, somehow for some reason the front camera features have skipped, but nevertheless, Honna Raju sir had already covered the front camera features of it already. So I would just skip it. So you can see here the orientations in which the cameras they can be connected. If you look at the car on the right hand side, the top view of it, you can see the various positions of the car where it can be mounted. Here you have the orange triangle or cones looking at the front side of the car, which is actually mounted behind the inside rear view mirror on the inside of the dashboard or the windshield. And then you have the surround view cameras which are connected all around the camera, all around the car, and some of them on the side rear view mirrors, which will look at different position. And also in some combination, the satellite cameras can be fitted on the A pillar, B pillar, and the C pillar. The A pillar and B pillar and C pillar are the pillars which are actually connecting the roof onto the chassis of the car. So the camera can be mounted in any different orientation, and still it has to perform the detection algorithms. So the detection algorithm, when I say, they are looking at the scenario, whatever it is detecting, like when we are driving, what are those things that we observe around the scene? Maybe it is a pedestrian, maybe it is a lane, or maybe it is a traffic light, maybe it is an animal, or maybe a person walking around. And also maybe we can also be looking at some certain things like advertisement signboards, and maybe even in a bridge or tree or something which catches our attention, we look at almost everything while we are driving. Similarly, the camera needs to also do the same thing and map it onto a real world. That is the objective of these cameras. That's all. The camera only does that. And eventually the central processing unit, like the ADCUs, the central controller units, which I mentioned earlier, they builds on the environmental model inside the brain or on the processor, and then makes a decision whether we have to drive in this way, or whether we have to apply brakes, or whether we have to further continue looking into the advertisement signboards, and probably we are interested in buying something while we are driving. So all such things have to be done while with the help of these analysis or the image grabbed from these cameras. So, but these cameras, they come with their own specifications. They can be with different megapixel imagers. They can be with different field of views. They can be with low light conditions, because these cameras, certain cameras, when we get into a parking lot, maybe the surround view cameras I'm talking about, the satellite cameras, they need to work in a very bad light condition where when we get into a parking lot, nothing much is visible there, even for the naked eye. So, but the camera should be highly sensitive enough to detect in the low light conditions also. So the hardware of these cameras also have different specifications depending on the usage. But this is only an introduction of all of it. But what really happens within the camera, that is the algorithms. These algorithms, the image processing part of it is mainly changing into deep learning technologies going ahead. So we have our 5th generation of the camera family coming to the cars right now, and in the 5th generation camera we have all the classical approaches way for detecting the objects and detecting the pedestrian, detecting the traffic signs, and detecting the roads and the lanes, and name anything, we can be able to detect them in the classical conventional object detection techniques, like the HOG features, the histogram of gradient approaches, or even many template matching approaches, and all those that we were doing a few years ago. And also earlier, motion from stereo, the structure from stereo was actually discussed by Deepu sir. He was mentioning about the concept of the motion parallax and so on. So we can build a 3D depend with the help of structure. Structure here means the 3D and motion. So while in the motion, we are building the structure. So there is a motion parallax. What is present in this frame? When the car is moving, it is already moved in a certain distance. So there is another image captured there, but we have already traveled certain distance. So this displacement and the two images, the previous image and the current image with a certain displacement, already creates a stereo disparity. And with this stereo disparity, we can also construct the motion, structure with the help of this. So that is another approach of finding 3D and also detecting the objects with the help of this structure. So that is one of the approaches that also is used in our 5th generation camera. And then we have the semantic segmentation, which is the deep learning approach based detection systems, which is also part of the current generation. So you can say name a CNN, that CNN is already there, and it is performing the task of detecting the objects and the buildings and the trees, person. You can see here the road is colored in a different, pavement is colored in a different color. Objects that are there on the road are colored in a different color. A person is colored different. And this is all happening and getting labeled on the real time on the cameras, which you can see on the left hand side here, the smart cameras, or the satellite cameras connected to the central processing unit. So this is how it does. And then all these detections happening from the classical approach, from the structure from motion, and also from the machine learning approaches, that is the deep learning approaches, they just get combined together and a map is created, and scene interpretation is performed eventually after that. So then we can say which part of it is the drivable road and which part of it is the road boundary where you cannot actually drive, and where you have to apply brakes if there is a pedestrian or a certain obstacle running in between on the road. So all this scene interpretation happens in the mapping part of it. So this slide actually talks about the core part of the image processing alone. What are the different stages? Earlier, that's the reason I snipped this slide from Honaraju sir's presentation, where he was mentioning about image acquisition to image pre-processing to edge estimation to strip identification to line fitting to, and then also he goes on to cluster generation and the tracking part of it also eventually. So not just that, now in our current generation cameras, as you can see on the top left side of the presentation here, there is an ROI selection and also pre enhancement or the image enhancement within the ROI selection, which we call as the pre-processing, and the pre-processing stage is also mentioned by Honaraju's sir's slide. And then we move on to the detection part of the algorithm, where detection happens in the classical image processing based approaches, where only the image is processed and the detections are done. And then the computer vision based approaches, where the motion cues are considered, or the stereoscopic approaches are considered to build the detect the objects from the scene. And then we also have the ML based or the machine learning based approaches done by the CNNs. So all of these, only if we look at the ML based approach, it can detect the objects on its own, or it can do a semantic segmentation with the help of CNN. Object detection can happen with the help of HOG features and other feature detection algorithms. And then monocular depth also can be done. All of these can be done in the based approaches. Then with the detections of image based approach and the computer vision based or the geometry based approach, you can say, and then the ML or the machine learning based approaches, image, geometry, and machine learning based approaches, they are all combined together. All the detections are refined and the clusters are generated in cluster analysis here. And these clusters are further continued to be tracked, and then actually is a refined object is said that this is a pedestrian, this is a traffic lane, this is a traffic sign, and a traffic sign of a particular type, maybe a speed limiting sign of 60, and maybe a traffic light saying that it is a red traffic light or a green traffic light or a yellow traffic light, and accordingly it moves on to the next stages. And those next stages, what happens in the sequence of the images, I will show in my subsequent slide. So here I have some snapshots only. Videos won't run here, but I have videos. I have videos separately in the hard disk, which I will also run and show in the real time. So here you can see the CNN based approach, and this is also a CNN based approach for the free space detection. That is, we are only detecting the free space within which a vehicle actually can move. And here in this picture, we can see only all the objects that are detected in one shot with the help of a CNN engine. And here on this crossing object detection, usually what happens is maybe this is a very unlikely condition in India, but this is in European region or in where the regulations are mandatory. We have to give way to the crossing traffic when it is means everyone knows whose priority it is, and crossing traffic, we cannot just get into and sneak into the traffic when and ever we wish to sneak into. So all these crossing traffics are also observed. So This is one of the application where crossing traffic is detected. And also the wheel and the wheel orientation of other vehicles in front of us are also detected. This is to detect whether the vehicle moving or overtaking us or moving ahead of us, are they cutting into the lane and merging into the road, or merging into the vehicle or not. For that, we have to detect the vehicle and the vehicle orientation, or the wheel and the wheel orientation and the angle in which they are turning. So for that also we have other applications. So then traffic, you can see here most of it is related to the pedestrian, and the pedestrian safety is the top one priority in case of advanced driver assistance system. So not just detecting the pedestrians, but also we have to observe their behavior. So to observe the behavior after detecting the pedestrian, we go into the skeletal based approaches to say whether the pedestrian is he intending to get into the road and walk crossing the road, or is he inattentive and looking into his mobile and crossing the road. Is he doing something else, or is he if there is a ball which ran into the road, and probably there is a likelihood of a child also running behind the ball to catch hold of the ball. All such scenario have to be estimated and predicted as well. So such kind of a thing also we have to take care. And here in the bottom right corner of the image, you can see the traffic police kind of a signal with the hand gestures are detected to detect the traffic police, and detect whether he is asking you that, or is he signaling you to go ahead, or is he asking you to stop and wait until the other traffic is cleared. So all such applications have to be embedded into our detection algorithms. So the position of the camera here, this is actually the picture of the rear view camera on the top, the bottom right corner. It is where it is mounted on just above the number plate, and it is detecting the pedestrian. And this is on the test track. That's why we are using dummies to detect the pedestrian, so that we don't hurt, because this is also detecting and braking also. So we don't hit the person and kill him. So we are using dummy on our test tracks. So this is some of the pictures of trailer hitched to it, but I will show the video on the demonstration. So usually on a architecture, this is how the image processing flow alone happens. So there is an image acquisition from where image acquisition, it moves on to the image pre-processing where the images are enhanced. And also these cameras are once fixed, and we only see or look at when, or rather we cannot maintain them always. So what if there is dust on the camera, or something is blocking the camera? All these are also inspected, and the blockage detection also happens to see that camera is always clear and visible. It is looking at it, looking further. So with this image, a pre-processed image, the optical flow happens, and from the optical flow uh, is your motion stereo, or the depth from motion happens in the next stage, that is the geometrical perception. Eventually also the image pre-processed image also pass on to the detection and classification for the generic feature for the generic feature extraction and recognition of the objects based on the machine learning approaches, and also on the classical image processing based approaches. And after that happens in the subsequent feature level happens of all the recognition functions. The recognition function, as in the pedestrians are detected, the lanes are detected, the traffic signs are detected, traffic lights are detected, traffic signs are detected, and the trailer is detected, trailer angle is detected, and so on. And further, these detections are passed on to the environmental model. We call it as a comprehensive environment model, where other sensors are also doing the same, like how camera is doing the object detection and passing on the information to SEM. Even the radar is detecting the objects and passing on to the comprehensive environment model. LiDARs are also detecting the objects and passing on their detections to the comprehensive model. And in the comprehensive environmental model happens all the scene aggregation or the object aggregation, and still and then also the association between this object and that object, and then one object is created and environment is mapped in the brain, like how we are looking in front of the means sitting in the cockpit, driver cockpit, and looking ahead, and with our visual perception, visual sensory organs, we are perceiving the entire world and creating a map. So maybe even if you close your eyes for a second, when the traffic is not dense, you can still imagine what is around and what is not, and you can still drive safely. And similar to your eyes as a perception, adding on to the environment model, you also have ears, you have other sensory extra six sense organs also, which are working together, which will also contribute to build onto the sensory organs there. So probably there is some animal shouting, probably you can sense that at a certain range there is an animal which might even cross the road, so you become extra conscious, and you are adding that animal which is not visible to your eyes, which has come through your auditory sensory organ. Also you place it into the environment model in your brain, and you start driving carefully at that stage. So that is the analogy I can give of the comprehensive environment model. The brain actually does the environmental modeling, and then what happens is in the next level is the driving functions. Driving functions is when you hear that sound of an animal and you sense that it might there is an animal, probably it might run into the scene any moment, so you start driving carefully. You will all of a sudden become very alert and apply brakes. Your leg will go on the brake and you start slow down the vehicle and start driving carefully. So braking happens and slowing down happens. Probably you did even see the animal also, and suddenly it ran into the picture, so all of a sudden you press the brake, and or you might even steer the steering angle and drift into a different lane so that you don't hit the animal. So all such things are called as vehicle functions or the driving functions, and that happens eventually. So this is the sequence of the flow of the algorithm, entire thing. So main part of the computer vision algorithms happen from this blue box of image acquisition until the recognition functions, domain specific recognition function, and only the objects are detected and passed on to the environment model. Environment model onwards, it's all about mapping, sensing, mapping, and aggregating from different sensors. You merge them as different objects. You perceive them as different objects, but still it means you detect different objects, but still perceive it as one object and map it and track it and take necessary actions. They are all the computation part of it. So this is mostly the deep learning. So what are those the detection part of it? I just snipped this slide from Honaraju sir's slide. That is the road sign detection, lane departure system, pedestrian detection, and vehicle detection, and so on. So this is what you can say is actually this orange block there. The camera which is looking front, that is the main camera, that is the smart camera. It can have different field of views, and at different field of view it does different operations. That's why I had it. But this one actually shows that there is a camera which does all these orange blocks, submits to the orange block. Similarly, there is an ultrasonic sensor connected to this comprehensive environment model, and also a radar could be there, or a LiDAR can also be connected. Going ahead, we will have this automated driving also, where in which there will be no driver inside the car, and still the vehicle is driven by itself, and parking is done by itself, and so on and so forth. So that is automated driving. Right now we are in advanced driver assistance system. So these cameras are right now assisting the driver to drive. So that's why we call it as ADAS, so the Advanced Driver Assistance System. But going ahead in future from 2023 and 24 onwards, you can already see some products in the market where automated driving is come into picture, wherein which there is no need of a driver to drive the car is driven by its own. This can also be already seen in Tesla cars already, and they drive by their own. So I have some videos for what I was talking about, the structure from motion. I will show. This is from our surround view camera portfolio, uh, that from the structure from motion, we are detecting the objects and looking at the drivable path. This is all the four images are processed together. There are four cameras connected all around the car, and this car is driven in the parking lot, and this is basically looking at the free space where the car can be run into and parked inside the parking lot. So this is purely the structure from motion based approach for detecting the object. So for example, what is that structure from motion I was talking about? I'll come to this picture here. So we have in the detection part, we have image based approaches, structure from motion based approach, and the machine learning based approaches. The video which I just showed was from the SFM, or the structure from motion based approach of detection of the objects. So I'll just show one example each for. So this is one of the classical approaches for image based approach for detecting a parking slot. So you can see here, images are processed, edges are detected, whatnot, and then you can start connecting the lines, drawing of transform, whatever it needs. You process in a sequence of algorithm and detect the lines and then parking blocks. So whatever it is detected, you can see in the bottom here, all the parking slots that are available are mapped here. So this is again for the surround view camera system, where it is used for parking, automatically parking within the parking lot. So stereo disparity map with the red block marked here, that is the region of interest. For this region of interest, there are two cameras which are connected. One is actually doing monocular depth based, means it is doing the monocular depth here with the help of a CNN. So CNN is performing the monocular depth map, and the below image you can see is the depth map created from the CNN. Deep learning based approach. But still we have two images here to validate whether means we have connected two cameras, but everything is happening in one camera. But the second camera we are just using to validate the stereo disparity created from stereo camera, and what the monocular camera is detecting, and validating on the real time whether the detection is correct or not. That's why we have two images, right and left, for the stereo also. That is only for validation, but mono camera is actually performing all that it is needed here. So depth map is created here. So what is green is the nearest region to the vehicle, and what is blue is actually very far away from the car, and the range between green to blue um, is actually the range that you can perceive in the different shades for the different distances here. So I have one example from our sister. Okay, this one is for the object detection, the debris object detection. On the left-hand side, you can see the drivable path and the 3D top view generated also of that. So the guardrails along the driveway is detected, and some debris on the road is also detected, and it is highlighted on the on the grid map here on the left hand side. So I'll just talk about the surround view valet parking, automatic valet parking from our sister company or the service provider company Electrobit. So you can see you don't see Continental here, but Electrobit belongs to Continental, and this is an automated valet parking application that is already being tested in our labs in Germany. You can see the person got out of the car and he used the tablet and he asked the car to go and park itself inside the garage. So nobody is inside the car. It is just driving on its own and going and finding its own parking slot, and parking by its own. This is how the view looks from inside while it is. So this is an application of automated parking. Here, cameras, surround view cameras, and also ultrasonic sensors are working in tandem to do this application, not radars. Ultrasonic sensors and 4 surround view cameras are used here. This is our test vehicle in our office. The person drives and gets out of the car and presses asks the car to go and park by itself in the real time. This is from the video from Continental itself. That one was from Electrobit. So he just leaves the car and gets into the office. The car will go and park itself, and after the end of the day, while he has to come out of the office, he will on his phone he will just say, come back, pick me up, and it will come and pick him up by its own. So this is only one application of valet parking. There can be thousands of applications like highway driving, where on a monotonous road you're driving thousands of kilometers while you're driving. You're just, you don't need human intervention. You don't need to hold the steering all the time. Instead, you can just turn on the highway assist feature and you can go to sleep and the car will drive by itself in the highway. So you just saw that a person walked in between the automated car, but still the car stopped, waited for him to cross, and then continued to drive. There is nobody sitting inside the car there. I'll skip it. So it just parked. So now outside the office, he asks the car to come back. So then it will leave the parked slot and it will come to pick him up again. So this is the connected feature. So the car will be connected to the high resolution maps, and it will tell, whenever you use the phone on the cloud services, that will instruct the car to come back. And that's the reason everything is connected, I said. With this small presentation, I hope I could show some practical applications of computer vision in automotive. Thank you.
Thank you, sir. It was a wonderful session on automotive application of computer vision. So, dear participants, our next speaker will be Dr. H.L. Shashireka, Professor, Department of Computer Science, Mangalore University, Mangalore. She'll be addressing on natural language processing of Indian languages from computer vision perspective. Over to Shashireka, madam.
Good morning, everyone. First of all, I would like to thank Murali sir for giving me an opportunity to be part of his team. I would like to try to integrate computer vision with natural language processing. Okay, let us consider the scenario. So, can you give me a caption? So we come across such photographs on Facebook, Twitter, Instagram, and so many online media, requesting or just asking suggestions for a photo caption. So what can be the photo caption for this? So we can give any caption. I mean, that is left to how we perceive the things. So a caption can be a cow is standing in the field, or it can be this is a close up of a brown cow, or like this. So you can have any captions. See, once you can give a caption like this, can we give a caption like this? See, the earlier case was a simpler one. It was just a cow standing there, but now here you can see the situations are different. This can also be considered as a situation recognition, whereas this can be considered a simple example of image captioning. So here you can see that the situations are different, but here the word carrying or the caption carrying now serves all the serves as a caption for all these images. But some may be the simpler ones, and some may be the a complex image. So let us consider another example. Can we caption all of these components? So here the captions are given like bottle of water, tablet, bouquet of red flowers, cup of coffee, banana slices. This is an example of dense caption. So what is important about these captions? Suddenly I have shifted from natural language processing to this computer vision, or maybe even the image processing. So that the importance here, or the significance of these captioning, is the input you can see is an image, and the output obviously is a text, and that is where we say NLP can be integrated with computer vision, or computer vision can be integrated with NLP. So the input is given as an image. It may be a simple image or a complex image, and the output is it may be a single word, or it may be a phrase like glass of water with ice and lemon, or it could be even much longer. So what we are trying to do here is given an image, right? Given an image, the input will be an image and output is a text. When we can do things for image, why can't for video? So can we have a caption for this video? The advantage of having video captions is we can give subtitles for a video clip. So this is an example of video caption, where video is given as input and the output is text. And this task is not that simpler compared to images, because a lot of things have to be considered here. And I'm not going into the detail like how this can be done. No, this is just to create a spark of how integrating um, computer vision and NLP helps to solve other problems, or the major problems that we are experiencing nowadays. Right. So this is another application, right? A picture from a dozen words, drawing board for realizing everyday scenes. So the input sentence, the earlier one was, in the earlier cases, we saw image as an input, video as an input, and output as a text. But here we have input as a text. When we can have image to text conversion, why can't we have text to image conversion? So here the input is a sentence. A group of skiers are together as they are ready to ski. So here, let us not worry about this box generation, shape generation. Finally, what is the output image? Because I do not know the computer vision part that actually happens. So that computer vision part is a black box for me. But what is given here as input is the text, and what we expect as output is the image, right? So where can we find the applications like this? Applications may be there. Given the description, you can ask a machine to draw. And one very important application that came to my mind all of a sudden is customized stories that suit the kids' imagination. So here I would like to mention that when my son was a small kid, he used to give me some characters, and sometimes I was finding it so difficult that how do we weave a story with all those characters. So now with machine doing this, it is possible to give any number of characters, whether they can go together or not, that may be a different thing. But when the machine is there to do, so we can give whatever characters we want, and maybe the situation also we want, and then we can think of generating the stories, because here the input is the text. So I'll give the text as the input, and the output can be the stories. That is, again, it can be in the form of a audio, or can we think of creating a video for that, or can we think of designing animations for that, or we can even think of drawing that scenario, right? So this can be a simple example or simple application of text to image conversion. So this is another example of drawing caricatures based on the text input. So given the text input, how do we draw this? And these are the realities that are happening today, but it may not be that accurate as we human beings do. So machine, I mean, when we human beings fail times, sometimes we still expect the machine to do better in almost all the cases, right? So this is another application, that is composing sketched scenes from test descriptions for interactive applications. Here also you can see that the input is the text description and the output will be a sketch. Usually in movies or in TV serials, we see uh, in the police station especially, the police personnel, they'll ask some victims or somebody who has seen the person, and to ask them to draw the sketch artist will be there, and the sketch artist will try to draw the sketch of a person, taking input from the person who has actually seen maybe the culprit or whoever it is. And this is also now a reality. So how it is done, again, I'm not going into this, but what interests me is I can give any description as a text, and then get the corresponding sketch for that. Right. This is another example. So if any of you are familiar with answering essay type questions, essay type questions in the sense, given an essay and given a set of questions, you should be able to answer to those questions by studying the essay. So in our school days, this was quite common. And if you are familiar with English grammar, then also there also we study about these things. But now in all this quantitative exams, this answering this essays is a must. So they'll give a small essay, and you have to and also the set of questions, you have to answer those questions by reading that essay. So when you can read the text and answer, where both input and output is the text, so why can't we have the image? So given an image and a set of questions, can we answer that? And the output now will be a text. So for example, here in the first image, you can see who is wearing glasses. So man, in the first answer is man, and in the second one it is woman. But as human beings, now we can do this without any difficult at all. Very easily we can say who is wearing the glasses. Similarly, in the second one, where is the child sitting? So the child is sitting on the fridge, inside the fridge, or the child is in the arms of the mother, or arms of a lady or a girl. Like that we can easily say. But can the machine also do this? Again, what is important for me here is what is input and what is output. So input is a image and also the text, because the question will be written in the form of a text, and the output should be in the form of a text. Again, now we are considering both image and text as input, and the output is text. So once we can do this for images, can we not do this for videos? I don't know whether it is possible. So some of the applications just came up to my mind, and I'm including all those in my slides. If you can do it for image, maybe we can also do it for videos, but the complexity may be slightly, why slightly? Complexity may be much more compared to the images, because as I understand, videos, video clip is nothing but a sequence of still images. So this is called as visual question answering. I mean, even the earlier one also is called as visual question answering. So here you can see, for example, if you consider this pizza, so the question is, pizza is given as an input, and the question is also given as an input, and the question is, how many slices of pizza are there? Is this a vegetarian pizza? So how do we answer this? So how many slices of pizza are there? That is quite easy compared to the next question, because if you look into this image, maybe we can make out how many slices of pizza are there. But how do we say whether it is a vegetarian pizza or not? So answering the second question may be much difficult compared to the first question. Then if you consider the image which is at the bottom of the slide, so does it appear to be rainy? Does this person have 20/20 vision? So how do we relate these two? So does it appear to be rainy? Now this may be somewhat easy to answer, because looking at the background image or the background contents of this image, you can see whether, you can say whether it appears to be rainy or not. But what about the second question? Does this person have 20/20 vision? So how do we know whether this person is having 20/20 vision? Just because he is holding a banana, can we say that this person is having 20/20 vision? Again here, the another one, which the picture which is green in color, is this person expecting company? What is just under the tree? So what is just under the tree is a simpler one, but is this person expecting company or not? So how do we decide? So visual question answering is a topic of research which deals with these type of images and the question answering. So here input is a image and a text, and output is a text. Again, once it can be done for once it can be done for images, I think it should be possible to give even videos as input, but computer vision experts should say what is the complexity of this particular research problem. Yes, and my interest is in text, and all these days, I mean, we have done several works on identifying the fake news. So in identifying fake news, this I also had mentioned in my talk on which I gave on 23rd on natural language processing. So fake news detection challenge, if you consider only that part, fake news detection challenge, so the input will be text, and based on text, based on the input, now you should be able to say whether the news is fake or not. And that is quite simple compared to the multimodal fake news detection challenge. And here you can see some of the images are given here. Not only images, even the text will be given as input. By considering both the combinations, now you should say whether the news is fake or real. For example, in the first image here, the image is given and we have some information about this image, that is Maryland Drive gets probation for Delaware crash that killed 5 NJ family members. So this is the text associated with this image. So here you can think of two kinds of work. One is as it is given here, whether to identify this image or this input as fake news or not. And the other one is, why can't we consider this text, Maryland Drive gets probation for Delaware crash that killed 5 New Jersey family members. Can we consider this as a caption for this image? So if you consider this as a caption for this image, then how we are going to caption this? What is the background information that we have about this image? So without any information, can we just say Maryland driver gets probation and so on? No. The best caption that I may give for this image may be the girls in uniform, but that also may not be a suitable one, because we have one guy which is also wearing a similar shirt. So maybe we can think of people in uniform, or people in red, or something like that. So given input which is both image and the text, So now the output will be the text. Image is input here, text is given as input, and these two have close associations because the text that is given here is the information about this image. Similarly here, if you consider the last image, it says this is an image, and the text says, I just thought that that was sitting in Delhi. So this is an imposter content. And similarly here you can say, you can see the manipulated content. So my plane hit an orca right after takeoff. So this is the manipulated content. You can see the labels for the given input. It may be true, it may be satire or parody, or it may be misleading content. So neuroscience says doing this one thing makes you just as happy as eating 2,000 chocolate bars. So this is a misleading content. This may be a manipulated content, a false connection, an imposter content. And again, you can think of any captions that we can give or any labels that we can give for these images, especially when it comes to fake news. And one point to be remembered here is that how do we actually make out whether it is true or not? If just the image is given, you can't make out anything because the image may be true. The image, as I said here, for the fourth image, my plane hit an orca right after takeoff. If this text is not given here, what you can make about this image? So can we say this is the actual thing, or it may be something else also? It need not be the same what is given in this text. So given only the image, it is difficult to classify whether it is fake or the real one. So for these images, we also need the text associated with this. And now comes the question of how we can process this, because we have computer vision algorithms for image processing, and we have text algorithms, or the NLP has got there are many algorithms for this, and we can process this text using the machine learning using text analytic algorithms, and for we have image analytics to process images. Now these two if go together, then uh, we think of classifying these images as fake or non-fake. Maybe that can be in the a coarse-grained challenge kind of thing. So in coarse-grained, it may be like the classification is a binary classification which says that this is fake and the rest and the other one is non-fake. But when it comes to non-fake, this may be a fine-grained which says that whether it is parody, or it is misleading content, manipulated content, false connection, imposter content. You can even add like whether it is offensive and so many other labels. Right. Another interesting one is trolls versus not trolls. Again here, it's not only text or only image. And what is so important about trolls versus not trolls? So why do we troll? So troll is just for fun. So not to target any individual or a community or anyone for that matter. But nowadays, what people are doing is they are misusing this. They are misusing this and they are targeting an individual or a society, and this can create negative impact for the society, which has to be avoided. And the other one which supports this troll is the online media, or the social media. Using the social media, you can reach these trolls to a larger mass within no time, and the ratio in which it spreads is very fast. And now you can imagine if you troll targeting a society or even an individual, so what will be the fate of such a person? So they may go to a extent of even committing suicide, or maybe depression, or any psychological problem may be the result of all this trolling. So what you have to do? So can we classify this as trolls and not trolls? So trolls, as I said, trolls is for fun. So the funny ones can be kept as trolls, and if it is targeting an individual, so they can be considered as the trolls, which are not the funny trolls. So first of all, you should be able to classify whether it is a troll or a not, because it may be the actual information or the factual information that is conveyed by this. The other one is a troll. So similar to the earlier one, here again we can think of having a coarse grain classification and the fine grain classification. In coarse grain classification, we can think of having troll versus not trolls. And if it is a troll, what kind of troll it is? Is it targeting an individual, targeting a group, or what type of false information is it conveying? So again, you can think of any number of labels for these trolls. And another point that we have to consider in these trolls is what is the type of information that is given as input. Here you can see, if you capture only the image and do image processing on this and try to classify it as trolls and not trolls, so it may not help, because in when you say training data, in training data we'll have positive samples as well as negative samples, but how many positive samples can we think of considering for trolls versus not trolls? So image processing alone will not help, or the computer vision alone will not help to classify these trolls efficiently. So there comes the natural language processing. So the text part of these trolls can be extracted and they can be processed separately, and then the image part can be processed separately, and the results obtained by these two can be integrated in order to say whether the troll is a troll for fun, or it's a troll which is targeting someone, or in the coarse grained one we can even say whether it is a troll or not. So you may even give an image or a picture like this, which need to be distributed among your friends, or maybe among the subordinates or the staff of your organization, so which may not be a troll, right? Similar to this troll is the other one is memes. Internet memes, they are quite common. Internet memes can also be considered as troll to some extent. Again here, when you say memes, it's not only the image part, it also consists of the text part. Again, can we think of considering this memes classification? And how do we do this? To do this memes classification, only the textual features or only the visual features does not help. See, in the troll here, you can see that there is some text here, but this text is in the form of a picture, or text is now part of the picture, and you cannot, to do NLP work, you can have to extract this text and convert that text into the editable text. So without this we cannot do NLP, because for NLP or text analytics, what is given as input is the text. For image, what is given as text is, what is given as input is the image. So in order to do image natural language processing or text analytics on this type of trolls, or even for the memes, first um, we have to extract this text and then do the digitizing part of this, or convert it into editable text, and then go for text analytics. Whereas for image, you can extract these images and apply the image processing algorithms on this. The same holds good for meme classification. And meme, to classify these memes, you can again go for textual or textual and visual features. Maybe in some cases, if text is not there, then we have to manage with only the visuals. And if visual is not there and only the text, then we have to manage with the text. But one thing that we have to note down here is text will not be in the form of an editable text. In order to obtain the editable text, we have to extract the textual part of the image, do OCR on that, and then get the editable text. And nowadays, the other project that is quite important is the digitization projects. The digitization projects is earlier it was like only for machine printed text, and in some cases for some languages even handwritten text can also be OCR'd in order to get the editable text. In simplest way, if I want to say this OCR or this memes classification, troll classification, so extract the text part from the image, and then do OCR. OCR is optical character recognition. So if you can bring that text into let us say a PDF form, or if you can have a bag of representation for those words that are present in this trolls or memes, or any image for that matter, so then we can think of applying text analytics. Right. So the digitization projects here, we can two applications that immediately come to my mind is, one is digitizing all the documents. So that is quite possible. So why digitization has to be done? See, if you're riding a vehicle, maybe a two-wheeler or a four-wheeler, or whatever it is. Now you have to carry a lot of documents. Like you should have your DL, you should have your vehicle registration, then you should have the what is that ignition emission test certificate should be there, then your vehicle insurance should be there. So all these are required. In addition to this, you'll be having your own documents, like you should have your Aadhaar card more or less all the time, and maybe some other documents are required all the time. So why we have to carry all this always? Instead, if you can digitize this, then it will be easy for us to carry the digital copy of all these documents. So that is one application. So similarly, there are some old books. Maybe we can even say that they are the treasure. In such cases, maintaining those old books is very difficult, and over a period of time, it becomes very expensive also, because every time we have to bind, and it will be exposed to it may be exposed to sunlight, it may be exposed to the cold weather, and because of all this, weathering of that book will be there. So to avoid that, what people are doing now is digitizing that entire book. So digitize that entire book, and entire book now should be available. So this is one example I gave. So a lot of information is available in this old books. So that also can be digitized. Then the other one is, if you go to a place, for example, if you go to Kerala, almost all the boards will be written in Malayalam. If you go to Chennai, almost all the boards will be written in Tamil. But if you go to Karnataka, if you are in Karnataka, then we can even manage without knowing Kannada, because many of the boards will be in English. But what about if you go to Kerala? It is very difficult. In such case, so what we want is take an image of that the board or writings, whatever it is, and then if you assume that if you have a software which converts this image to text, then we can easily read the text, provided we translate it to some other language. And now Google Translator, it supports many Indian languages. So capture, for example, if you look into the image which is at the bottom of this slide, it says stop. If I do not know English, if I do not know to read this, then what I can do is you capture this image and give it to the there are two steps, in fact. Yeah, first is you have to extract this text part, convert it into the corresponding word in a corresponding language, and then this should be translated to the language that you can understand. And here you can also think of cross-language translation, cross-language information retrieval, because if it is some other word, then you may need some additional information, and if that additional information is not in your own language, then you have to search in the documents, in other documents, and then convert those or translate those documents into your own language. So this is one slide I got from some paper. I'm sorry, I couldn't make out. I couldn't save that paper. Because of that, I'm not able to show from which paper I have taken this. So this is where, or this is a scenario which says vision meets NLP. Here you can see, I'm not going about this, because vision people they know about reconstruction, reorganization, and recognition. And NLP people, they speak about this syntax, semantics, and pragmatics. But for me, what is important is what is there at the bottom of this. Here you can see on the right corner, you can see an image, right? An image here. And at the left corner, you can see a text. So for me, what is important here is, so given this text, so can we think of getting a image something like this, or given this image, can we get the text which is something like this? You may not get the same the text exactly if you give this image, and again if you give this input as if you give this text as input, we may not get the exact image. But to what extent we can do this, right? So this is where we have to think of using computer vision algorithms, and think of using text analytics or even the NLP algorithms, and we can go together to solve many problems, right? So these are some of the references. I think I end here. So thank you.
Now I request Dr. Geeta Kiran, Professor and Head, Department of Computer Science and Engineering, Malnad College of Engineering, Hassan. She will be delivering on application of computer vision in agriculture. Over to Geeta, madam.
Thank you. Good afternoon, all. I would like to take this opportunity to thank Dr. Murali S., my PhD guide, for giving this opportunity to talk in this esteemed short-term training program. I'll be now talking about applications of computer vision in agriculture. In the next few minutes, I'll be talking about the role of computer vision in agriculture, the areas identified, automating agricultural process using computer vision, the main issues being addressed, and I'll take up a case study, what I'm working with, that is the yield estimation of mango fruit crop, and end up with the innovative startups in agri sector. So why to choose the field of agriculture? Yes, that's the main question. That is one of the most important sectors of the Indian economy remains agriculture. That is the reason we go and choose and work on the field of agriculture. Let us see the sector status in India. Growth of socio-economic sector in India. It is the process by which any nation, or in India what we are talking, by which in India improves the economic, political and social well-being of the public. So the socio-economic development, it is the process of improvement in a variety of ways. It has to influence all the aspects of human life in the country. So you can see it is a means, the agriculture is the means of living for almost 66% of the employed class in India. And also it has acquired 18% of India's GDP and occupied almost 43% of India's geographical area. And if we go back in the 11th five-year plan, the irrigation facilities was given the major role. That is, huge investment was made for the irrigation facilities in the 11th five-year plan. And also we are now seeing the deregulation in agriculture sector, where lots of two pros and cons are going on, debates are going on, like whether it's to take on or not. So this actually opens the competition for the agriculture products. We know that there is more demand for agriculture, but we are not able to supply that much of it. So this opens the competition for agricultural products. and removal of unnecessary restrictions is necessary, like movement, stocking, and so on. So we have to go for the good price to the farmer, and substantial technology will be grown in the coming years. The identified areas for enhancing the agriculture sector, mainly we have taken into it as three categories: one, monitoring; the other one, decision support; and the third one on the AI interest. Yes, this agricultural crop condition, with the implementation of agricultural artificial intelligence, farmers can analyze the weather conditions, temperature, water usage, and soil conditions collected from their farm to make decisions on the business choices, like determining the most feasible crop choices that year, or which hybrid seeds, decreased waste, and all those can be identified. So the agriculture industry is looking to maximize the efficiency by turning to artificial intelligence technologies. So artificial intelligence technology has been implemented to help yield healthier crops and reduce the workloads, organize the data, and to improve a wide range of tasks. So we are now very much knowing about the precision agriculture. So this uses the artificial intelligence technology to aid in detecting the diseases in plants, pests, and poor plant nutrition on farms. And also the big data analysis we are talking about nowadays determines the optimized irrigation, and it helps reduce the greenhouse gas emissions and pinpoints the exact soil, light, food, and water. So if I go on telling, there's a lot of things as I have pointed out here also. It is the agricultural crop conditions, weather, climate, ecosystems, and also the agricultural planning and policy making that's going on, and the computational intelligence in agriculture and the environment, an expert geographical information system for land evaluation, and also AI, where intelligent environment control for plant production systems. We have boards nowadays in agriculture, and also artificial neural network for plant classification using image processing, and also to control the greenhouse effect. So this precision algorithm is using AI technology to aid in detecting the diseases in plants, pests, and poor plant nutrition on farms, as I said. So AI is solving the critical farm labor challenges by augmenting, we can say, or removing work and reduce the need for large number of workers, where this agriculture bots, the robots, harvest crops at a higher volume and faster pace than human laborers, more accurately identifying and eliminating weeds and reducing the cost and risk. So the crux of the smart farming is always having a blended farming. That is, we having both digital, which help alongside the traditional forms and tools. Next, I'll talk about the automating agricultural processes using computer vision. As I already mentioned somewhere here and there, where the field robots, which is used to automate the process such as harvesting, planting, weeding, phenotyping, that is identifying the best breeds by monitoring the growth and identifying the phenotypic traits that signify a robust genotype. Livestock identification, which identifies the stock and monitor their growth and provide information about progress towards the harvesting, and also on grading and sorting, where it is actually combined with deep learning techniques nowadays. So machine vision can sort good crops from bad crops. That's also going on. And machine guidance, where the computer vision is used to guide autonomous tractors and other vehicles in variable outdoor conditions. So the main issues to be addressed are
plant and fruit detection approaches, harvesting support approaches, fruit grading, ripeness detection, fruit counting, yield production. All these are the main issues to be addressed. These are really a good research problems which we could take up. So camera types used for machine vision in agriculture, vision-based vehicle guidance systems for agriculture applications, vision-based autonomous mobile agricultural robots we do have. So I'll take the case study, that is the mango fruit crop yield estimation using machine vision, which we are working on now. We have come out with this yield prediction of the mango fruit, where we have selected the mango fruit crop yield estimation using machine vision as our research problem. We have created our own data set. The data set, it consists of images of mango trees obtained with the camera is nothing but the camera of the mobile phone itself, that is OnePlus A5000 dual camera we have taken. So that was under natural daylight conditions with an image resolution of 1920 cross 1080 pixels we have taken. And the data was collected for 5 months temporally in an interval of 7 days for the first 3 months. Then the frequency of data collection was increased for a subsequent 2 months based on fruit maturity. Then 800 images for a day was captured, which includes images of 5 trees. We have taken 5 trees. So the images were captured in 2 sessions, namely morning and evening. So this was aligned with the direction of the sunlight. Further, we have captured these trees from a distance of 2 and 3 meters also. So the selected trees were from the orchid, they vary from 15 to 20 years of age, and the trees range with the height of 7 to 8 feet from the surface. This was all the pre-processing things where the data set was collected, and totally the data set was around 21,000 images altogether. So the Horticulture College at Mysore helped us a lot to collect the data set. That's what I have mentioned here. To go a little in detail, I'll not take much of the time. I know we are running out of the time. So steps carried out was, we took the image and the noise was removed using the Gaussian filter, and the color features of the mango tree was analyzed with the RGB color model itself, but it was very difficult to take out to segment the fruit from it. So this image was expressed through histograms, but using the RGB color space, we removed the background image, and then taking that background image, the segmented image, that was taken as an input where we applied for the HSV color space, which helped us to get the fruit segmentation where we could get the fruits. So the data acquisition was, I was telling, like we had in 2 directions, northeast and southeast direction, and we had taken in 2 distances, 2 meter and 3 meter, at morning 9:30 to 10:30 and afternoon 2:30 to 3:30. That was what we had maintained. And this was the images of the mango tree at a distance of 2 meter that was captured, and also the 3 meter capture. And this was how the background was removed using the RGB color model. See the result. We have the input image, the background removed image, and based on the image histogram, we have fixed with the threshold taking 50, and we have removed. And this is the fruit region segmentation, what I was telling about. So here again, we have taken the saturation. And this was the segmented results what we have got. And now we are working on the circle fitting and fruit counting of the same, where we have applied O transform, ransack 2D fit and circle detection based on object geometry methods. and we are getting better results for the hoe transform. You could see it here. This is a circle fitting based object geometry and the ransack 2D fit. And this was the results what we got from the hoe transform. And now whatever we had done now until a quick thing where we took totally 30 fruits as of now. The correctly identified were 23 and we have false positive 6 and 7 were missed. So you can see the percentage and you can see the chart given, the comparison of the manual count and automatic count of mango fruit yield estimation. And now to continue with, we are making use of, to get better results for the yield estimation, we are analyzing using deep learning. So color analysis method for the yield estimation, we know that it has some limitations. So to predict yield at the early stage of the fruit maturation, now we are going with the deep learning with the pre-trained networks. As you all know, we have many of the pre-trained networks, AlexNet, GoogleNet, ResNet, and all. So we are getting, as of now, better results with the GoogleNet. We have to work on it. So as the data set has been built by us only, we are training for the classification and trying to detect the objects there, recognize the objects. The classifiers used, you can see, so the results are compared with the pre-trained networks, and totally we are using 5 different cultivars. So actually there, though we have taken 5 trees, actually we have only 4 varieties of mangoes in those particular 5 trees. So the deep learning model for this cultivar classification and the mango fruit detection is being developed. I hope will come out with good results. So I'll end up with taking a notice to the innovative startups of AI-based hybrid solutions for farm data collection and management. So whatever we do, whatever the research we do, we should come out with some products, we should come out with some innovative startups. There ends our work where we could reach the society. So there are some startups which have come out, which I have taken up. We have 4, as I noticed, the Brazilian startup and an Indian startup, a Swir Vision, and Exxon developed. Exxon, it is developed by Solar Zone. So Brazilian startup, the functioning of it is they provide the farmers with diagnostic information about the land and crops. The major features they provide is diagnostic information collected from sensors placed on the tractors or other equipments. Okay, so Indian startup here, the functioning goes like this: reducing the food loss and labor cost involved in post-harvest cycles in agricultural commodities. Coming to the features, provide automated grading and sorting solutions using computer vision and machine learning. The Swir Vision, which is with the high definition cameras, they deliver visible to Swir band wavelengths between 1.4 to 3 nanometers. They hold the sensors to provide vital agricultural services like water stress and moisture measurement and irrigation control. And one more I found was when I was just searching with this innovative startups, it was with Exxon developed Solar Zone, where the solar powered autonomous flying vehicle cover up to 200 acres at a single flight. Found it interesting. So the features here, the HD images provide the farmer with a piecewise view of critical farmlands. The multispectral images capture detailed crop and soil conditions to monitor the diseases. Hope I rushed to the things I have covered as I promised with the role of computer vision in agriculture, the areas what we can identify, how it could be addressed, and with the case study the taken yield estimation of the mango fruit crop, and ultimately how we could go with the innovative startups in agriculture. Thank you.
Thank you, madam, for the informative session. I now request Dr. Mohan, faculty member at School of Computing, Information and Mathematical Sciences, University of South Pacific, Fiji, to present his address on tools and data set for computer vision and machine learning applications. Over to you, sir.
Very good afternoon to all the participants, the organizers. And so I'd like to get into some of the topics. I mean, the topics of this presentation is like tools and data set for computer vision and machine learning applications. This is actually an intention to present this kind of topic is keeping the researchers, the people who are into entering into the PhD and continuing their PhD or research in computer vision. I would like to talk about something on where they can start working on, particularly the development tools and what kind of data sets they can use it for, pursuing their research. Actually, I got into my computer cognition technology in the University of Mysore in 2001 as a master's student. When I entered, the only option for us was C programming to do any assignments, programming assignments. Particularly when I attended Dr. Murali sir's digital image processing class, we had an assignment to solve signature verification using C programming. So we used to code everything to the core. The only image format that we were able to read was only BMP. So that from that time onwards, I just come to now and see the growth of computer vision. Those days when I talk about computer vision, pattern recognition, and machine learning, image processing stuff, people were more inclined towards the networking. So when I say about those computer vision stuff or graphic stuff, nobody cares about it. But now I'm surprised. I'm really pleased to see most of the people are into the machine learning, the computer vision stuff. So what's happening here, particularly in terms of the platforms of computer vision, is that the computer vision has brought much needed revolution, which is in terms of the computing platform, the software development, the research community, the open source community, all of them together. So the development in terms of particularly the GPU, the machine learning devices, and the platform that supports the machine learning or computer vision. In fact, even over the cloud, you don't have to invest heavily on those computing resources. If you are smart enough, it's good that you can choose cloud-based services, and they are really impressive. So these are capable enough to handle voluminous of data. That includes your time temporal data from the video sources. Actually, this is what is more consuming, particularly when I compare my own experience of starting the learning, particularly the neural network and soft computing approaches. We used to run the neural network algorithms overnight with simple, PC, the Intel PC, Pentium PC. We used to run the training process overnight during those days, and then come back in the morning and see whether it has trained or not. So that's how we were with the computing resources. But now it's a matter of few seconds to even do the deep learning. So some of the libraries that I would like to recommend, particularly into the computer vision applications, is that the OpenCV, which is well known, more than a decade old. It's been integrated into many of the programming tools like C++, Python, Java. If you are good at any of these programming, you can straight away start with the OpenCV. You also have TensorFlow, the Google's machine learning and deep learning library, which is very popular these days. It also has execution of prepared models that are tuned for particularly these pictures, the audio, speech recognition, object detection, even the reinforced learning and recommendations. If you are good at MATLAB, as you all know, you can still work on that. MATLAB has progressed a lot with the toolboxes which are available for this computer vision and machine learning applications. You have CUDA, which is by NVIDIA for parallel computing. If you are for keen in using the GPUs and parallel programming, you can use the CUDA. You have Theano, which is a Python-based numerical library, which can run on either CPU or GPU. That's also quite popular. And you have Keras, another Python-based deep learning library that combines best of all the libraries. So it has gained its popularity as it combines the power of TensorFlow, Theano, and CNTK. You can see the architecture of Keras. As you can see here, this is on top of the Theano and TensorFlow. And you have some of the libraries called SimpleCV, which has been recently introduced. This uses a lot of computation libraries with OpenCV. You don't have to worry about too much the concepts of computation. Instead, you can start directly working on your computer vision code. Most of the computer vision fundamentals are covered in this one. So experimenting in the computer vision using any of your data like images or videos, even in fact, this supports live feeds from webcams and some of the gaming consoles like Kinect. It is the best framework if you need to perform some quick prototyping. So you don't have to worry much about the coding. So you can start quickly prototyping your ideas. In fact, this is available for almost all the platforms like Mac, Windows, Ubuntu, any as you are familiar with. And you also have YOLO. YOLO stands for you only look once. This is a real-time object detection system. This is extremely fast and accurate comparing to other object detectors. This is as very fast. It looks the whole image. So its predictions are informed by the context of the image. It actually classifies, this actually identifies the objects and labels them. And also you have the MoveCV, which is also an open source library. It's written specifically for the real-time computer vision. So this also includes the lower level image processing, feature detection, and tracking. In fact, the camera calibration as well. You can also extend this for the 3D geometry. And some of the APIs that probably you can use, one is the Cloud AutoML. AutoML surveillance is also available, or AutoML vision is also available. So depending on your application, you can choose any one of them. The advantage is that this is available in cloud. Also, you have the Vision AI. You can see there's an example in this link. In fact, there's a video I have shared since the time is short, so you can just go through this. This runs for about 4 minutes. I just wanted to show you a small demo on how advanced this Vision AI is from Google. In fact, you can load any image immediately. It applies your vision algorithms and tries to classify and detect the objects in the scene. Right, so this is a picture just I loaded. You can see what it actually shoots and it detects from this picture. I have not chosen any context for this picture actually. So it says this is University of California, Berkeley. And also it gives where exactly this has been taken with the map. So that's the landmarks. You can see the different labels over here. So it identifies the face in the picture. It also identifies the objects, the different objects in the picture you can see. This is the image that I have loaded. You can see on the top, there are different tabs. The first one is the landmarks, which gives where exactly this picture has been taken. And you can see the faces identified in this picture. The objects, it says there's a person, there's a building, there's a glass. Then you can see the different labels attached to this picture. And also there's a logo. You can see from the t-shirt, there's a Reebok logo. And you can see the text that has been extracted automatically. You can see only REE is visible. The rest of the characters are not visible, so it is reading wrongly, but that's the visible portion. And the safe search, for example, if you have some images that are not good for the kids or whatever it is, so it says whether it is safe or not. It says, adult is very unlikely, spoof is very unlikely, violence is very unlikely, or whatever. So You can load the image and see how it classifies immediately. This is actually an example or demonstration, but actually this can be extended for many other applications. So this is when you go for try. So what's challenging when you go for the libraries is that choosing the right library, for experimentation, it's okay. But when you go for serious prototyping, serious research outcome, then you need to stick on to certain libraries. So you have to start working on finding out, depending on what your requirement is, accordingly, you can choose your library. And the data set that I'm going to cover the next part of the slide, how to choose the data set and what kind of data sets are available for the researchers. Also, you can create your own data set. Most of the data set, if you see, people have put a lot of efforts in creating such data sets, and then based on the data set, they come out with a lot of publications and benchmarking results. So if you are in a place where you could actually create a data set, in fact, when I was working with Murali sir, we tried to create a data set for constructing 3D models from the 2D images. I used to run around Mysore with a camera, digital camera, and then take the pictures of all those, ancient buildings, try to construct the 3D models of that. We were trying to build the data set, but then we stopped it after my thesis is done. But then once you create your data set, you'll be able to set a benchmarking for your computation applications. So what is actually required out of the data set you need to know. And then finally, do you really need such massive computing? Suppose if you just apply a simple face recognition or whatever. So you need to use simple computing resources and the other resources. Don't waste your resources or your programming platform in case if your application is very simple. Moving on to the next portion of my presentation, which is on the data set. I just quickly go through this because most of you probably might have come across this data set for computer vision. One of them is the MNIST, which is some of the the numerical characters which are used 0 to 9, which are formatted in 28 by 28 grayscale. The data is pre-split into training set, which is like 60,000 for training, and then test set for 10,000. This is used only for the fundamental computer vision projects, like if you are trying to recognize the numerals. The other one is the fashion MNIST. This is again 28 by 28 with different classes, like 10 classes are available. Those classes are fashion related, like t-shirt, top, trousers, pullover, etc. And then you have the CIFAR 10 dataset and CIFAR 100 dataset. This has 60,000 of images in 10 different classes, which consists of airplane, automobile, bird, cat, deer, and etc. And the CIFAR 100 is similar. There are also 60,000 of images in total, but there are actually 100 classes. The previous one, CIFAR 10, stands for 10 classes, and 100 stands for 100 classes. So the 600 images per each class is given. So this is again formatted in 32 by 32 pixels, pre-split into a set of 50,000 for the training and 10,000 for testing. And you have the IMDb wiki dataset, which has about 520,000 of face image scrapped from the IMDb and Wikipedia. You also have meta information like the face location of the image, the name of the person who's in the image, date of birth of the person, the gender of the person, all those things. This is usually used for gender prediction and age prediction tasks. And you have the ImageNet. This is created jointly by the Stanford and Princeton for a computer vision competition called the ImageNet Large Scale Visual Recognition Challenge. The participating teams were challenged with 5 main tasks like the object classification, object localization, object detection from video, and scene recognition using the ImageNet dataset. So this was actually built based on another one, which is called as the WorldNet. This was a lexical database for English, where only nouns are selected. Over 500 images per each node of the hierarchy has been created. More than 1.4 millions of images, over 220,000 classes are there. This is one of the largest classified image datasets available and open to the public. So if you want to make a very robust algorithm in terms of these 5 tasks like object classification or detection, so you can use this as one of the benchmarking data set. And you have the Pascal OC, which stands for the Pattern Analysis, Statistical Modeling, and Computational Learning Visual Object classes. This is also open sourced by Pascal, a research institute funded by the European Union. Images from 4 main topics, including vehicle, household, animal, and person, are available in this. This is further divided into 20 subcategories. They're widely used in early development of object detection and segmentation. So if you have an algorithm which runs at the prim level, then you can use this. And you have Label Me dataset, which is developed using the Label Me, which is an open source annotation tool. This is maintained by MIT, generally used for image segmentation. And you have the Microsoft COCO. COCO stands for the Common Objects in Context dataset. So this is published by Microsoft. That includes the object detection, segmentation, person key point detection, stuff segmentation, and caption generation. So this has about 120,000 of images with over 880,000 of tags. There are 91 categories available in this. Again, the number of images per such category is at least 5,000, which allows the machine to learn the detailed characteristics of each classes. So again, you can use that as one of the benchmarking data sets if you are developing an algorithm on those classes. Places 2 database. This is another data set released by MIT. This has about 10 million images and over 400 scenes. So this can be used for the scene classification and scene parsing. That's about the data set. Actually, you have plenty of data sets. If you keep looking for the open source data sets, there are plenty of data sets available for your machine learning and computer vision applications. So you can actually start from the fundamental one if you are starting to learn computer vision. If you are an advanced user, you can keep some of the advanced data sets like ImageNet to keep the results as the benchmarking results. So what are the challenges in this data set is that basically identifying the data set based on your purpose. So basically you identify your purpose and then go ahead with choosing the data set and benchmark your results. Don't try to generalize. Your algorithm may not work in some of the data sets. The only thing is, depending on what exactly you want, try to be specific to those data sets and try to get the benchmarking results. And always good for learning and benchmarking. These data sets, most of them are for ideal or standard conditions. So it's not been tested on some of the scenarios where poor lighting conditions and the obstacles and things like that. But this has been tested for ideal or standard conditions. So if you're writing an algorithm, ensure that you are assuming that your algorithm also works in the standard conditions. The issues in creating own data set, as I told you, creating a data set includes standardization, publishing in some of the portals like Kaggle, and then benchmarking, and you always have to scale it up when you create a data set. So keep that also in mind when you're creating your own data set. Actually, being in India, we have a lot of potential to create a data set, particularly these for the autonomous vehicles, for the object classifications, particularly the food classifications. We have a lot of potential. Thing is that we need to standardize them. Once the data sets are available, you need to keep track of them because they also keep updating. And then once you use these data sets, ensure that you come out with the robust algorithms, which always outperforms the best of the recent publications working on those data sets. All right, so that's it. I'm done. Thank you so much for the opportunity.
Thank you, sir, for the informative talk. I thank all the speakers of today's morning session for the informative session on various research domains in computer vision. Now I request Dr. Murali sir to give his concluding remarks on today's technical session. Over to Dr. Murali sir.
Good afternoon to all of you. Thank you very much, all my dear students and participants for making this event a grand successful, because the last day itself actually you had 7-8 lectures. So that's the speciality of the last day, concluding day. So congratulations to the entire team for coordinating. So 2 things out of this to be taken from the session. One, see, whenever you are doing research kind of activity, even after PhD, and completing 10 years of service. Actually, people still are there in the same research area. So that is the strength of my team. See, most of the time people, migrate and switch over to some other kind of research. But all this people who professors, they have delivered lectures today, they were in computer visions even when they were doing PhD, even after their completion and maybe so many years of completion of their PhD, still they are in the same research area. So that is the speciality of the team and the attachment with the computer vision. As I indicated in the beginning, computer vision is not something black box, which is the unique opportunity for all of us to just understand how exactly human being does in all this activity. Just imitation of this may not be in a single algorithm, or may not be God is so gracious to give a single algorithm to do everything, but we are trying to impose so many. As Dr. Mohan mentioned, there are many such kind of tools. So there are plenty of things to be developed and being developed. One message to be taken, as I mentioned, actually, even after so many years, all these people are doing similar kind of work. The second thing, even I used to mention to all my students that for guide, actually, it's a learning. It is not that actually guide is known with all knowledge. Even I used to say when they were doing research, I am learning along with you. It is proved again today that actually all my research students have done extensive research, which is a learning lesson for me. Even, for example, Geeta Kiran explained about computer vision in agriculture, but that's a news for me actually. That's a learning for me. So that is how the spirit of the research is. I learned many things. Even Dr. Mohan, when he was doing research with me, used to say, "Sir, we need to come out with a data set." And the way in which he explained today, even many things were not known to me. So such is the kind of learning that any researcher should keep in the mind. It is always learning. It is not that I have completed my PhD and it's the end of research. So I'm very fortunate that all the people who are presented today, so just they are still in the research. And even, for example, Dr. Shashireka, natural language processing, actually she connected with computer vision, and later I'm seeing through the group that lot of discussion still going on in the WhatsApp group, that actually this is how we have correlated computer vision with natural language processing. So that is the beauty of research. So therefore you should be able to take many things, get connected, and see that actually it is as vice principal of this college mentioned, we need to disseminate it to our next generation stakeholders, to the society. I congratulate Dr. Sharmila Kumari and Professor Ganesh Pai and all for making this event a grand successful one. Whenever you require any sort of support from our end, we will always be there. Our team will be there to help in computer vision. And thank you very much for listening.
Thank you, sir, for your concluding remarks.